So good morning everyone. This is lecture number 11 E211 analog circuit design. So we were talking about current mirror in the previous lecture. We also learned that in current mirror there is something called current sink and current source are there, and we can design it using NMOS and PMOS accordingly. We also learn about various things like what is matching of the transistor. We also understand what are the identical transistors. Identical means exactly same, and then for the matching purpose you may use multipliers or you can use fingers. Generally, like in the industry, people are using multiplier just to make sure that there is possibility to add more transistors afterwards if they need, or using fingers generally. And fingers has an added advantage of having a smaller periphery and area, which you can found out by just simply looking at width and the length of overall transistor, and they are going to overlap each of the fingers, so where each of the gate is acting as one finger. And in multiplier, those number of transistors are in shunt. Similar thing is happening in finger. However, in the case of cadence, there are various terms like width, length, multiplier, finger, and width per transistor, or you can say that some equivalent name, effective width per transistor. So width might be, let's say, W, L is L, multiplier, if it is some m number of multiplier, means those many transistors are in parallel and you have to make them separately. Whereas in fingers, let's say there are f number of fingers, then effective width per transistor, considering m number of multiplier and width of W, it's going to be equal to m divided by f times W by L, by the way. That will be effective width per, sorry, I should write down just this one because the unit of this one is meter. This is also in meter, Yeah, so we talked about this and we understood that usage and how to use it. All these things are clear to us. On top of that, we studied that the simplest current mirror, which looks like this one. So by keeping the appropriate ratio between two transistors for any load, you can have the current flowing through each of the transistor as I, if it is just both the transistors are same. However, if the transistor has some multiplier, that much amount of current will be flowing from the other transistor. And we also understood that every current source, if current source is given to you, you have to find out or you have to evaluate whether it's good or bad. There are only two parameters which we need to see. First one says that the source impedance has to be infinity and the minimum voltage has to be 0. So we know that that can be done by the simplest technique, which is cascoding the transistor, right, or cascoding the stage. So by doing this, we also agree that here it's V on plus VTH. That's why this is only V on. This is again V on plus VTH. So looking from this point to this point, it's 2V on plus VTH, 2 VTH, and that's why across this one it's 2 V on plus VTH, and this also tells us that across M1 we need to have V on plus VTH to make this transistor in saturation. This is a minimum number, and we also learned that V on has to be more than some 250 millivolt to 300 millivolt, or more than 300 millivolt will help you. This is the number actually known to us, right? So now we learn that the simplest one is good in terms of V minimum voltage, but source impedance side, it's not infinite, it's R0 only. And in the case of this guy, which is folded cascode, it's GM times RO square. So in that case, of course, cascode is the winning one. However, in terms of V minimum potential, this is not the minimum voltage. We are seeing something like almost like 600 millivolt plus some VTH, which is a large number compared to the previous one, which was just around 300 millivolt. So it's all about how much headroom do you have. You have only the headroom till VDD, or you can say the VDD plus VSS, that's your headroom. So this technique is also not the good one. So let's look at some ancient technique, which is known as Wilson current mirror, found out by the guy called Wilson. And this is better in terms of basically in terms of the stability or the current which you are achieving, how much deviation you can tolerate. So if this is M1, this is M1, and this is M2, and this is M2, you can see that there are two places where there is a negative feedback. First of all, we know that from gate to drain potential, if you are connecting, it's actually a negative feedback because the gain is negative from this point to this point. If I increase this one, there is decrement will be observed over here. If I increase here, the increment at source side will be observed over here, maybe with some gain. But so this notation tells us that from here to here this is negative feedback, and from here to here, if we are going to connect it, it's positive feedback. So in this case, there are two transistors M1 and M2 which are here. So gate is tied with the drain, gate is tied with the drain, so it's showing the negative feedback. So here you can say that the current flowing through this branch is I. Then because of this connection which is tied over here, and from here to here we have some potential. We are not going to declare it now how much potential, we have to apply our theory. So the the potential seen over here, according to that you can have here voltage which is VTH times lesser than what is available here. While doing this, let's understand this, that the current flowing through both of them, like both the transistors, are I, and while doing this, this is also I. So if that is the case, the current flowing through both the branches are I and I from both sides. Once this is achieving I, looking into this side, actually it's 1 by GM, and this side it's RO. So it will replicate this current this side. Look at this. So earlier we were replicating this current to this side, but here it's replicating this current to this side. And we assume that the initial condition is 0 earlier, but after few iterations, or maybe after t equal to 0 plus, this current has been replicated over here. That might be some change, or it might be some delta I. Let's call this one delta I. So now here it was I, here it's I plus delta I because of so many reasons. One of the reason is source impedance, another reason is the voltage output. So all these things will not give you guarantee that the current flowing through here it will be I, but it will be some delta I. So if this is I plus or minus delta I, because this potential is fixed, same potential is available at the gate of M2 of another side, you can not have the current as I, but it will be replicated as I plus delta I, and this transistor is going to demand the current to be changed from I to I plus delta I, and that is going to be flowed from here. Of course, it has to change this dynamics also, and according to that, other side will also change, and like as time gives the permission, like at the end you are going to have the stable current because of two negative feedbacks. So it's not only one side which is going to be corrected. And note that this current is actually realized with a resistance where this potential is going to be changed, and that's how like this delta I is getting accommodated. Otherwise the infinite impedance resistance based current does not have such effect. So in reality it's a resistance, and that's why like this potential Vx and Vy are going to be changed, or Vz. So all these potentials are changing, and hence they are going to adjust themselves for I plus delta I at settled time. So this is a good in terms of having the exact current mirroring which we want. So in this case both branches will have the exact current, whereas in previous current mirror which we are talking, so from this one if it is I, this side it will not be I, but it will be I plus or minus delta I, and this delta I will be depending on the fact that source impedance is not infinite and V mean is not equal to 0, and moreover the potential which is from here to here is not exactly equal to the potential at the other side. So these are the main sources of error. So you can call it VDS1 is not equal to VDS2, right? So VDS1 is one side of saturation potential, and others is another side of VDS potential. So this is happening to us and we can't help it anymore. So this might be the better technique, but to find out each one of the current mirror, we need to look at one thing very clearly, that whether it's qualify for our requirement of being a good current source or not. Those requirements are source impedance and V minimum to be 0. So looking from here, the source impedance or the resistance Ri out, if this is M1 and if this is M2, this is a cascode connection and it's equivalent of this particular configuration. So from looking from here, as this is diode connected, I am supposed to see 1 by GM2, and for this one looking from this side, I am supposed to see GM1 times RO1 times 1 by GM2. So it's that much, GM1 times RO1 divided by GM2. So now this is a resistance which is not comparable to the previous case, which is GM times RO square in the case of Cascode. And if both the GMs are equal, then it's turned out as same as the previous simple current mirror. So that is also one of the case. We need to make sure that GM2 is as small as possible compared to GM1, right? And that can be achieved with the one fact that you have to increase width. So note that if you want to increase GM or you want to control GM, you need to change the width, because by changing the width, the resistance is reducing and GM is increasing. Whereas if you are interested in finding or improve channel length modulation resistance, you need to increase length. So these are the thumb rule. Okay, so in this case it's not so much winning one, but let's see what is happening for the second case, whether it's giving you the required voltage or not. So let's look at this carefully. From here to here, it's V on plus VTH, right? As this is connected in diode configuration, across this it's V on plus VTH. Okay, no problem. What happened to the second one? So from here to here, or you can say from here to here, it's again V on plus VTH. So if you're carrying a multimeter in your hand, and if you measure the potential between these two, I'm going to see two voltage sources. Each one of them is V on plus VTH. So I'm going to see two V on plus VTH effectively. So if I am looking at across this entire transistor whose gate is connected to 2 V on plus VTH, I should see 2 V on, sorry, it has to be 2 V on plus 2 VTH. It has to be 2 V on plus VTH. Interestingly, in that case, this transistor demands only V on voltage. By the way, these are the bare minimum required potential to make these transistors in saturation, right? So in this way, it's comparable to the Cascode, but it's not as good as regular one where we used to have only V on voltage as V minimum voltage requirement. So as per the feedback theory, it is winning one, and this is giving you the stable current whatever we want and with the minimum error. But as per the as per the evaluation criteria, it is not giving you better results. So let's move to the further one, and let's see what is happening. So one of the configuration which was taken from, by the way, these all these configuration and things are copied from or taken from one book called Alan Holberg. So this is one of the good book you need to read, as I told you in the previous lectures also. So the next one is the configuration where you have like this. Okay, so this is another configuration which is taken from the book. So here you can see that I have like I have determined that if I want to have a good current source which has two characteristic, source impedance is infinity and V minimum as 0, we learn that the better technique is actually Cascode in terms of source impedance. However, we are losing in terms of V minimum. So in the source impedance, we were seeing Gm times Rho square in the case of Cascode, and V minimum as V on 2 V on plus VTH. This is what we have seen. So I'm saying that we are not going to do that. We are going to allow my circuit to have 2 V on at the output. So let's fix this, that I am going to see 2 V on. I fixed it, right? And I know that each one of the transistor needs at least V on voltage to be in saturation, right? And we are choosing this configuration because still it's cascode. Look at this. Because of cascode, we are achieving good source impedance, which is, looking from here, it's GM 1 times RO 1 times RO3. If GM, like both the transistors are identical, having all the conditions same, then it's GM times RO square. That's the impedance or resistance you are seeing from this terminal. And I fixed it. I want to see only 2 V on. I don't want to see 2 V on plus VTH. So we can do the back calculation, which says that here I need V on plus VTH. Yeah. And if this is V on plus VTH, this potential from here to here, it has to be V on plus VTH, right? Because it's available from here to here. So if I am holding a multimeter which has V on plus VTH, I'm supposed to see V on plus VTH across this. And I know that if this is V on and this is also V on, then the current will be the same one. So whatever the current flowing from here, which is IREF, same current will flow from here when it's both the terminals, both the things are identical. So this is what I am doing. But notably, the required potential over here, it's becoming VTH. Look at this. This is very important to understand this. And if that is the requirement, or that is coming from here, you can't avoid this transistor to be in cutoff. This is not in saturation. For the saturation, you need at least VDS set or V on potential, which is more than 250 or 300 millivolt. Maybe VTH might not be that much value, and you are ending up with something where this is out of saturation. In that case, you need to use here depleted mode transistor, or still like with this technology, like you can use a M2 transistor which is having VTH, and still you can keep it in saturation if that VTH is a big number. So there are two conditions: either you keep it in depleted mode, or you keep, or your threshold voltage is too much. Okay, so that is one thing. If I am seeing here 2 V on at this transistor, that big transistor which is composed of M1 and M3, I'm supposed to see here 2 V on plus VTH. As per our theory that says that if the gate is 2 V on plus VTH, it has to be 2 V on plus VTH minus VTH, which is going to give us 2 V on. So across this transistor, we should maintain 2 V on plus VTH. So this particular scheme is advantageous in terms of good source impedance, and also like minimum potential is now 2 V on. It's not adding up threshold voltage, because that is a bare minimum thing which we can do. Otherwise, the things will be difficult to keep every transistor in saturation. And so the trick is as follow. You have to do that one. So this was one of the configuration taken from the book which I told. Other than that, there is one more thing, that rather than doing this, we can add like one more resistance over here to make it self bias. Okay, let's look at this. Okay. So by adding one extra resistance over here, name it as R bias. Instead of having one extra branch for this transistor, I'm calling this at using some R bias, and the current flowing through this branch is IREF. Notably, this IREF is not normal IREF. You can have some resistance through which you can find out the required current flowing through the branch. So we have fixed the current flowing through this one as Iref through this current. Notably, we also require to have two main characteristic of a good current source. Source impedance has to be infinity, V minimum 0. We found that the better one is this one, where you are keeping it cascode. So still these two transistors are in cascode, right? So the resistance looking from here, it's GM2 times RO2 times RO1. If both are identical, then you can write down GM RO square. Yeah, so that resistance we are achieving, and as I told you, like in the normal cascode we are getting 2 VDS plus VTH. However, we want to make it only 2 VDS. Let's assume that condition. So V on is actually equal to VDS, which is written here. So we are not going to write this because, yeah, so we are going to have 2 V on across these two. To achieve this 2 V on, you need to have 2 V on plus VTH at the gate of this one. So if this potential is 2 V on plus VTH, we left with one fact that if this is V on, this gate is requiring V on plus VTH. If this is V on plus VTH, this in total we require V on plus VTH potential. So you have to design it such that one of them has V on, one of them has VTH, and vice versa. For that you might need depleted mode transistor, or you can use the threshold voltage which is much higher than what is required, or 300-400 millivolt, then it might possible. So from here to here, if it is V on plus VTH, and if this is 2 V on plus VTH, we need to make sure that across our bias we need to see V on only, and notably V on has to be 300 millivolt or some number which is more than that, such that all the transistors coming in saturation. So if we are doing this back calculation in such a way that we are going to get V mean as 2 V on, and the source impedance is same as the cascode one, which is GM RO square. So still it's a winning situation, no problem. It's similar to the previous one. The advantage compared to the previous structure is you don't need require one extra current current branch which is going to contribute in power, or that is going to definitely will give you extra added power of VDD times whatever the current is flowing through this one. Let's call it I1. So that extra current you have to burn, and it's all about the it's all about just a game of current and power, right? So we need to avoid that. Now what we learn is from two required parameter, which is z is equal to infinity and v mean equal to 0. From previous all particular things we learn that it's very difficult to achieve v minimum less than 2 v on for very good source impedance. Of course you can add more cascode like this. Instead of, we can have an argument that let's have not only one, let's have like 3 triple cascode, where like VB1, VB2, VB3 all are DC potential which are actually generated from here. Might be like this, or maybe from self bias configuration which we have seen just now, or maybe some other way you can generate VB1, VB2, VB3 separately also, and here you can have, from looking from here to here, you can have 3V on plus 3 VTH, and you can have here 3V on plus 2 VTH. Let's assume that for this technology VTH is around 250 millivolt and V on is already fixed around 300 millivolt. So in that case this number will be 900 millivolt plus 250 millivolt. So this becomes almost like 1.15 milli 1.15 volts across only these three transistors. And if your supply voltage is around, if you are working at 5 volts, things are fine. But if you are working at 1 volt or the latest technology, this cascading business doesn't work because your headroom is limited. There is no point in adding so many transistors in cascade and achieving very high high impedance at the cost of V minimum potential, which is not zero. Now it's reaching your headroom. So how to manage it? You may have some depleted mode and other things. You can do some uh, lucrative things, but at the end, it's going to be difficult to keep all the transistor in saturation to get the best out of each of the MOSFETs. So in that case, what we can do is we can adopt one new technique to improve the output impedance without losing the bandwidth or without having any problem with the headroom. Also like headroom or common mode voltage requirement will be nullified. There is no problem in this case. And that technique name is gain boosting technique. So in gain boosting technique, what I mean to say is, or some people also call it regulated cascade. Let's assume that you have such a scheme like this, and here it's a regular current mirror. Definitely I need to keep one more transistor on top so that it becomes cascade, and it is going to give me a good gain of or good gain in terms of resistance as GMR RO square. However, GMRO square is not sufficient enough. As I told you, like this number is turned out as something like 20 kilo or 20 kilo to 100 kilo. I like to have it something in mega ohm. And V minimum potential 2 V on plus VTH is possible generally in such kind of scheme. But we can also achieve 2 V on also, as we have seen in previous two configuration taken from Alan Holberg. So in that case, what we can do is not only one transistor which is M2 is connected on top of M1, which is the cascade connection, but I am taking this gate input via one amplifier whose gain is GMA times ROA. So if this is some V in at the gate of this one, this is GMA times ROA times V in. If this is the case, looking from here, it's adding one more impedance. So from going from here to here, the effective incrementing resistance is not only just this one, but it's GMA times ROA times GM2 times RO2. I'm not going into detail for the derivation, but this is what you are going to see because it's cascading of two amplifiers together. One is GMA-RO and another one M2 whose intrinsic gain is GM2 RO2. So you are going to have this in particular this loop. But if you are looking from top, where you are going to have this kind of configuration. So from here to here, it's effectively GM2 times RO2 times GMA times ROA. And here, looking from here, we know that looking from drain side, we are going to always have RO1. And looking from here, we should have GM2 times RO2 times GMA times RO8 times RO1. So the both the impedances are going to be multiplied. This is what we need to do. So now we also know that intrinsic gain of the transistor is GM2 RO2, which is this is what we are going to see here. Similarly, if GMA ROA, if I want to implement it, I can take a small common source amplifier, right? And when we are saying common source amplifier, where we are keeping here current as a load or whichever current you like, you can keep that, whose looking upside impedance is infinite, because current has always impedance of infinite. Then this particular configuration is going to give me GMA times ROA in minus, by the way. Okay, so that's a mistake over here. So GMA RO, GMA ROA, and that is going to be multiplied with GM2 RO2, and in whole we are going to have the resistance of GM2 RO2 by this transistor times GMA times ROA times RO1. This is what we can do, right? So you can see here only this term, if it is giving 20 kilo ohm, and if this is something like 20, you can have something like 400 kilo ohm or zero point 0.4 mega ohm. At least we are in mega just to cheat our eyes or our brain, we are keeping it 0.4 mega ohm, right? So if you want to have, like, if you are greedy on R outside, don't take just GMA ROA, but take some. You can have two stages also. You can improve this gain, and you can have it not only 20, you can have it 100 or maybe 1000, whatever you like, you can keep it there, and you can achieve that, and you can have the higher resistance of at the output side. Okay, so now there is another configuration, but notably I forgot to tell you over here, but the across this one we are going to maintain 2V on only. So this is going to be 2V on. This is what we need to achieve, or at the worst case you can have 2V on plus VTH. If you don't do any lucrative thing which we have done in the previous slides, so you can either achieve 2V on plus VTH or 2V on. You have to, like, some different variations of such schemes are already available, so you can see that, and like many people have published many advanced version, but the most important part is I'm just discussing the bare minimum configuration which is required to understand, so that, like, you can build it up on top of this one. So in that case, you can make many configuration, like, so you can make almost like 10 different configuration which can achieve 2V on, or also it can achieve 2V on plus VTH, right? So now there is one more. It's also using regulated current mirror, like here. So now this is a differential amplifier where there are two inputs, plus and minus, which is similar to what we have seen in op amp, right? So if this is V in, I'm fixing this for V in, because the most important part in any amplifier or anything is, it's all about how much you can drive it. So it's about the driving capability or the power gain. It's not about always just voltage or current which is playing the role. Let's say if we are doing this, that 1:n ratio transformer. So a transformer is not an amplifier. if you're looking at the the resistance and voltage, in terms of voltage and resistance, you will see that actually the power wise it's same at the both side. As you are increasing number of turns, the resistance is actually getting decreased, and like, and because of that you are accommodating the voltage. So in that case, both side power remains same, and it's not amplification. Whereas in amplifier, what we want is, for any value of resistance, I want V out much larger than V in. This is what we are going to call it amplifier. Not only from such configuration where by keeping or changing the resistance value, it's changing, and that's why we want that for any voltage control voltage source amplifier, we want that R out is as low as possible. So for zero value of resistance itself, I want to see the amplification, and the zero resistance is not possible. For standard practice, we can call it 50 ohm. So for that, there is one configuration. Generally, people also call it low dropout or LDO. So you can study this separately, but in that we want to have the constant current for a constant voltage. So what I'm doing here, I'm keeping here at the plus terminal V in, and with the negative terminal connected here. So this is a negative uh, negative feedback. In that case, this is V in, this is V in. This is V in, this is V in, because of the negative feedback and the golden rule we can apply. So this potential is fixed to V in. It doesn't matter. You are going to see always across this one V in, right? And I'm keeping one loop or the feedback loop where I'm mirroring the current. So here it is ref, Iref, and this side it's N times Iref, which is flowing through this transistor whose drain is always connected to V in because of this feedback loop. And all these are the NMOSes. And if this is V in, you can even fix how much potential is required here on the basis of the V bias potential. So if you are fixing here as V on, this will be V on plus VTH. That is what V bias we want. Or if you fix something else, accordingly this potential will change. So for fixing the minimum potential over here, V on, you can design it with V minimum equal to 2 V in. Sometimes it's not sufficient, then you need plus VTH also. However, this is quite possible thing. But the source impedance here, looking at source impedance, this is going to give me, let's call this one as A0. So gain of this amplifier times GM2 times RO2 times the impedance or channel and modulation resistance offered by M1, so RO1. Notably here we are, when we are saying n times M1, we are increasing the width, we are not doing anything with the length. Look at that, the length of these two are identical, and to have better RO1, we already agree that we are not going to keep the minimum L which is required for, let's say, for technology of 180 nanometer or maybe even smaller technology like 28 nanometer technology. L minimum available to technologies, let's say 28, then we are not going to keep it 28, but we are going to keep it at least 3 times or 4 times, right? So if this is 3 times, this will be also 3 times. So in that case, this one becomes 3 times W divided by 3 times L. This is the unit identical transistors. However, to just match them, we are going to use the multiplier as N. This is what we are going to do so that you can have the better matching and better better things can be achieved over here. So now concluding on what we have studied on current mirror, because that's the end of our discussion, and we have studied various kinds of current mirrors. One of them was simple one, another one was low voltage. So if you remember, two circuits taken from Allen Holberg with the self bias resistance, and another one which has extra branch of current, those were low voltages. So, and we also studied regulated cascode, and we have studied cascode, Wilson, and triple cascode also. So of course simple has impedance of RO, and V minimum as VDS set, or maybe you can call it V on, whatever you like. For the case of low voltage, we have achieved 2 V on, and the impedance was GM times RO square. For the case of regulated cascode, it was same, but now this is increased by GMA times ROA. Whereas in the case of Cascode and Wilson, where Cascode was giving you GM times RO square, and Wilson was giving you GM1 RO1 divided by GM2 impedance, and V minimum as 2 V on plus VTH. Of course, as you are increasing the cascode, triple cascode, or four cascodes or five cascodes uh, in a like cascaded manner, then you can achieve better and better. So it becomes GMRO, not only square but GMRO times, like this is going to be increasing, something like this, right? So you are going to have, and if this RO, so as many number of cascode you are doing, 4 cascode, 5 cascode, so you are going to have GM times n minus 1 times RO n. This is what you are going to achieve, but at the cost of V minimum. So there is a problem with the headroom, which we have already seen. So keeping everything in a table, the simple current mirror has R out as minimum, as the source impedance, and VDS as V on. By the way, look at this, all these VDS are VDS set, and those values has to be more than 300 millivolt, or maybe some more than 250 millivolt. This might be working. This number might be higher than what is written here. Just to make sure that all the transistors in saturation. VT is the threshold voltage, and that's depending on the technology. So here you can see that various numbers and various things are written. So generally, like low voltage are better one, or the regulated cascodes are better one, which you can use it if you need the normal one. However, most of the time, like simple is also sufficient enough. You need to find out how much resistance is required for your case, and considering low voltage technologies nowadays where the VDD is 1 volt, people are still using simple one, or you need to do something with different transistors. You need to use a somewhere like depleted mode and other things you can use it. Yeah, so I'm concluding this whole chapter, which was current mirror. We are going to start with other things like frequency response after this chapter. So that's the next one. So thank you very much for today.